Alright, we've looked at the motion of charged particles from the point of view of equations of motion. You can also do it in terms of energy, which is actually easier in some cases. So if you think about to your energy stuff that you've done with projectiles or the motion stuff you've done before, you've got a rock there that you could actually lift and do work against gravity to lift up and change its energy. So the work done would be Fs, which is the definition there, the force, and to displace it in the same direction. And that would be against gravity, so MAS here is what you're working against, the weight of it, MA or mg. And you're going to be, let's say you had a 50 kilo rock there, and you're going to move it up against gravity of 9.8, and you might move it, say, 10 metres. Alright? So if you do that, it'll take a certain amount of the work or a certain amount of change in energy that's going to go on. So looking at that there, you get 4, 9, and it's 500, so it's 4,900 joules. Okay, so that work will be done up against the gravitational field, and that will convert into potential energy at the top. Okay, so it's got potential energy at the top, gravitational potential energy in this case. Now don't forget then that there's a formula for gravitational potential energy you used last year, mgh, and that was a direct link to ma and s, where the height was the displacement. So that's where that came from. So there's a certain amount of potential energy when it's that high off the ground that you would have got. Obviously when the rock is allowed to fall, you'll find that the potential energy turns back into kinetic. So that as it falls down, you'll find halfway, half of it will have been converted back into kinetic energy there. So half of this will be kinetic energy, and half of it will be potential, and so on. By the time it gets to the bottom here, just as it strikes, it's going to be all kinetic energy, the 4,900 joules. And you could, from last year, work out the speed of the rock by just using energy considerations and equations rather than equations of motion and the acceleration due to gravity. Okay, so this is another way of doing it. So can you do the same sort of thing if you were doing electrical fields, and we did a uniform electric field here where we had a positive plate and maybe a negative plate, and we moved a charge like a proton up to there. So let's say we tried to move a proton, and we have a distance there of maybe 10 centimetres rather than metres. And we look at the potential difference here, maybe we'll do 50 volts versus 0 volts here. Okay, so not a negative plate, but a 0 volt plate. So according to the formula, we should be doing work equals Fs, same as before. Now this time it's an electrical force, so EQ could be used here rather than MA. And the distance is going to be this distance here, which is often given the symbol D, the distance between the plates. So you could use QED there to work out the work done to move the proton from the bottom plate to the top plate in joules. And that would be electric field strength. Now electric field strength is actually delta V on D. You've got a formula for that. 50 divided by 0.10 times by, so that's the electric field strength formula, delta V on D. The charge of the proton, 1.6 by 10 to the minus 19. And the distance you're going to move it, which is going to be, D is 0.10. And you can see the 0.10 here cancels, so it's not actually important the distance between those plates. So you end up with there 50 times by 1.6, which is 8.0 by 10 to the minus 18 joules of work. So if I was to ask you a different question, how much potential energy, electrical potential energy, does a proton have against that bottom, that top plate that you would release if you let it go? It would be the same answer. That's the amount of potential energy it would gain if you moved it up through the field. The work done will cause a conversion of energy, and you'd end up with potential energy of that much there. So obviously if you release it now, the amount of kinetic energy at the bottom would be the same value, 8.0 by 10 to the minus 18. And you could use that with the kinetic energy formula to work out how fast it hits the bottom plate. So this is a totally different way of finding out the speed as it hits the bottom plate here. You're just using energies. So rather than use the acceleration formula we did in the last video to find out its acceleration due to the electric field, and then work out V equals VA plus AT, and things like that, and we don't have the time here, we'd have to use V squared equals VO squared plus 2AS. That's the one we'd use here, we haven't got time. Instead of doing those there, you could just work out, here's the work done here, there's a change in energy, and you could use it this way around. 8.0 by 10 to the minus 18, and you would rearrange for V. And that's another way of getting it to work. Okay? Using the mass of the proton. Alright? No, 1.67 by 10 to the minus 27 for a proton. Don't forget to square root it. Alright? Now if you look at this formula in a bit more detail, we've got work equals delta V on D for the electric field, Q the charge of the actual item, and D as the distance between the plates, or the distance going to travel between the plates. So you can cancel these out then. The D's are not important here. So there is another formula for work. It's work equals delta VQ. So the amount of work done on a charge would be based on its charge and how much potential difference you move it through. Now that could be compared here to this sort of idea here. The potential energy gained as this one goes up, okay, is based on the potential difference you move through and the charge, whereas the potential energy is based on the mass we're moving and how much gravity and how far you move it to get to the top. So very similar ideas, and this will be the potential energy gained as it goes up, okay? It's also the kinetic energy it gets back when it falls down. So this is just another way of doing it, very similar to the falling objects that are masses. All right. So let's look at that as an example using this one here, work equals delta VQ. Before I do, if you take yourself back a bit further in your unit of electricity there was a definition for potential difference or voltage. We said it was the amount of energy supplied to a given quantity of charge of, say, Coulomb. 6 volts meant that we supplied 6 joules of energy to each Coulomb of charge when we did electricity last year. Okay? So 6 volts means 6 joules per Coulomb, 12 volts means 12 joules per Coulomb, and so on. And if you look at this then, don't forget that energy is the same as the work done here in this case. So that's equal to the work done on the charge, okay? Which means that the work done is equal to the potential difference times by the charge, which is what we're saying here in year 12. Okay? So as long as you have that potential difference and the charge, you can work out the work done by the field, which will be the same as the potential energy being lost, converted to kinetic energy gained. Alright, so let's just try a couple of those. So here we have an electron placed between 2 parallel plates. So it's got a uniform field. The top one's got positive 1000 volts, the bottom one's 0 volts. So the electron's placed here, which means it's going to be able to accelerate towards the top plate because it's negative. So the question they could ask you is calculate the electron's velocity at the top plate. So one way of doing this is to work out the electric field between the 2 plates, then find the acceleration between the 2 plates, and then go and use an equation of motion to work out what's going on there. So then you would use V squared equals dA squared plus 2AS. So that's the sort of steps you have to go through to get the velocity at the top plate. Can you do it by terms of energy like I've just said though? So the electrical potential energy here that's going to be lost as it's released from here is going to convert into kinetic energy. It's going to be gained as it goes up there because it's going to accelerate. And that's equal to the work done, which is delta VQ. So if we do that, we've got delta V is 1000 volts times by the charge on an electron. So it's pretty quick to find that out, 1.6 by 10 to the minus 16 joules. So now that I've actually worked out the amount of kinetic energy you should have here, all the way at the top, because it should be equal to the electrical potential that it started with, we can now go and do a half mv squared and just rearrange for V. And this will also give you the velocity, probably a lot quicker than the other method. So doing it by that method is obviously a bit quicker because I'm just using one formula, second formula, as opposed to 1, 2, 3 here. So even just for a simple one where you're just going to let it accelerate upwards the electron and find out the velocity at the end, that's a fairly basic way of doing it. If we just look at some examples of this now, the ion drive is one good one where you've got 2 plates or 2 grids in this case. It's got a positive grid and a negative grid at the back of that, and so you've got an electric field in between those which is uniform. So the charges here that are being done is the xenon ions, or xenon atoms rather, are ionised by the electron gun. They become positive, and you can be accelerated between the positive grid and the negative grid and gain kinetic energy due to the work done by the field between the grid. Alright, so let's look at an example of that. So if you're told that the xenon ions have got a charge of +1 there, so that would be the same as that of a proton, 1.6 by 10 to the minus 19. We've got a positive plate here, there, and negative plate. Let's say we're going to put, say, 3000 volts of potential difference between the 2 plates. Can you work out the exit speed of the xenon ions as they go through the back? So again, you're going to do this idea of work done, or the kinetic energy gain, is equal to the work done by the electric field, which is delta VQ. So in this case, we've got a potential difference of 3000 it's going to go through. Charge of a proton is the same as the xenon one there, and you've got 4.8 by 10 to the minus 16 joules. So to work out the speed again, you're just going to go half mv squared is equal to the k. The v would be root 2k on m. So you're just going to put that number in there and get a velocity value in meters per second. Now if you do it the other way, by equations of motion would be quite hard because we haven't been told the distance between these plates, so you would have been stuck finding the field strength to start with. You could have done it in terms of d, I suppose. And then to work out the acceleration is equal to eq over n. I haven't told you the mass of the xenon ions, so you need to know that in both cases here. So we'd have to, I'll actually give you the mass of the xenon ions to work that out, and the same thing here. And the other thing then is you'd have to work out v squared equals vo squared plus 2as. So I still think this is a quicker way of doing in terms of energy considerations. All right. We're going to look at the cyclotron next, which is a bit different, because the cyclotron is basically a particle accelerator. What you've got is two Ds here, and then between these Ds you're going to release a positive ion, which is going to accelerate between the plates here, or the Ds. And the reason it's going to do that is because one will be momentarily charged positive, one negative, and this positive ion, could be a hydrogen ion, will accelerate across this uniform electrical field that is set up between the two Ds, and it gains kinetic energy due to the work done by the field. And you might just say, okay, so it's just going to accelerate at once over this little tiny distance. But what actually happens in the term 2 part of the course is we learn that there's a magnetic field here as well, and what that does is turn the charged particle when it gets on the other side. So this charged particle gets to here, will now turn in a semicircle because of the magnetic field, and it will cross the field again. And in the meantime, these two will swap. And so accelerate again, and you'll find that it spirals out, which is getting faster and faster, and gets to the sort of speed you need to get a nuclear reaction happening to make medical radioisotopes. But again, they could give you a question here where you're told the potential difference between those two plates is, say, 5,000 volts, and you need to know how much kinetic energy does it gain on each cross. Well, it's pretty easy to work out. The kinetic energy gained at each cross is equal to the work done, which is equal to delta VQ. As long as you know what the charge is on the ions and you know what the potential difference is between the plates, you can work out how much energy it's going to gain on each cross. So let's actually do this for a second. 5,000 times by 1.6 by 10 to the minus 19. You're going to get 8.0 by 10 to the minus 16 joules. Okay. Now you'll notice that all these ions and electrons and protons have got very tiny values for their energy. Such a small amount of energy, and it's quite hard to work with. So another unit that was defined here is called the electron volt, and it's a really small values of energy. So electron volt, I mean energy could be done in horsepower as well, by the way, but the electron volt, 1 electron volt is the amount of energy gained by 1 electron moving through a potential difference of 1 volt. Alright? So in other words here, 1 electron volt is equal to, now what's the work done on 1 electron? 1 electron would be going through 1 volt, be 1 volt from the voltage, potential difference. The charge of an electron is 1.6 by 10 to the minus 19. So you've got 1.6 by 10 to the minus 19 joules. So what this unit allows me to do is say, instead of using 1.6 by 10 to the minus 19 joules, I'm going to call that 1 electron volt, 1 EV. Now that actually means here that rather than saying this is 5,000 or 8 by 10 to the minus 16 joules, I could shortcut this and say I'm not going to do that. I'm just going to say this is 5,000 electron volts of energy. Okay, it went through 5,000 volts, it has 5,000 electron volts of energy. So it's a very handy unit to work with if you try to understand things. If I told you that you had a battery that was 12 volts and the electron went through the battery there and it said how much energy would it gain, you would go, it's got 12 electron volts of energy. If you have a pair of plates there, which has got 100 volts and 0 volts, and you'll release the proton, does that work the same? 100 volts has gone through, 100 electron volts of energy. So you can use that for protons or electrons or anything with a charge of plus or minus 1 electron. Okay, it's a very easy unit to use. So if you were using that, it's easy enough to say the work done on this here is equal to delta VQ. It's 200 electron volts. You can say it straight away without doing any calculations. All right, and that's going to be the kinetic energy gained. You have to be careful here. If they say what is the speed of, say, a proton that's released from there and ends up going to this bottom plate, that's its kinetic energy when it gets to the bottom here. Yes, But to work out this velocity, you'd have to go and then convert this back into joules, because you can't work with electron volts if you're trying to rearrange an equation. So how do you convert from electron volts back into joules? Well, you have to times by the charge on an electron. And that's what you need to be careful of here, 3.2 by 10 to the minus 17 joules, and then you can find your V. So just be careful that you can't use 200 electron volts into equations there. It's a good thing to understand what's going on, but in the end you should convert to joules if you're going to try and find out the velocity. Okay, thanks.